Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. I know 16.5 was rough. 16.5 is officially a doozy, but we are now finished with Chapter 16, and we are starting Chapter 17, which is the last chapter of this class. Everything else we need to do in Calc 1 is going to be contained in this chapter, and mostly it's about doing weird integrals in weird spaces, so that'll be very exciting. The weird spaces that we're going to start doing integrals in are called vector, some of them are called vector fields. If they're two-dimensional, then they're vector fields. We're also going to do some cool integrals in vector spaces, which are, Suna, excuse you, I'm trying to record a video. Suna wants to say hi. Suna. Okay, now let me finish. Okay, we're going to do some integrals in vector fields, which are two-dimensional, vectors all over the place in 2 dimensions. We're going to do some integrals in vector spaces, which are 3-dimensional, vectors all over the place in space. And the good news is we have some experience with vector fields. I've mentioned this word before. We talked about vector fields a little bit when we were talking about gradients, because the gradient of something is a vector field. Let's talk about that. We were doing stuff with, I think, chapter 15. We were doing stuff with f of x, y equals some function. Let's have something let's do something that's cubic in y and negative linear in x. Here's your function xy. It gives you some surface in 3 space. You plug in any point you want, any pair of xy coordinates, and that will give you a height on the z-axis, and that altogether makes a surface. And we talked about the gradient of f of xy being, the gradient of something is the derivative with respect to x, I, the derivative with respect to y, j. Or I'm saying i's and j's. I should say negative 1i plus 3y squared j. And this, we said, was a vector field. You could plug in any xy coordinates just like you could into a real function, and instead of giving you a height on the z-axis to create a surface, this will give you a vector on the xy plane. So this is probably a poor example to start with because it doesn't depend on x. So let me change it around a little bit. We'll make this a negative x squared. So you have negative 2x here. This is negative 2xi. Okay, now we have a vector field that does in fact depend on both x and y. So this, I think, will be a better example for us to play with. To get a sense of what this vector field is like, I'm just going to plug in a handful of points. So I'm going to plug in points x and y together, and they're going to give me a vector, del f. So good place to start is 0, 0. That gives me the 0 vector. If I plug in something like 0, 1, I should get 3j. If I plug in something like 1, 0, I will get negative 2. If I plug in 1, 1, I'll get negative 2, 3. I could plug in negative 1 and negative 1, and that would give me 2, comma, positive. No, it wouldn't. Negative 1 is going to give me, it will give me positive 2x here, but it'll still give me, yeah, it'll give me positive 3y there. Yeah, we're good. plug in 2, comma 2, I'll get negative 4, 12. So, the general idea here matches the general idea that we have whenever we're presented with a function and we're not sure what it looks like. You pick a bunch of points, you plug in your points, you figure out what the function values are, and you graph those things. In this case, our function values are not numbers. Our function values are all vectors. And we can still draw this. We're not going to get a three-dimensional surface like this thing is. We're going to get a field. The entire xy plane is going to be covered in little vectors. And we're not going to draw them all because there's infinitely many. That would take too long. But we can draw enough that we have sort of a decent idea of what this vector field looks like. So at 0, 0, we have the 0 vector. That's fine. At 0, 1, that's this point here. Our vector is pointing 3 in the y direction. At 1, 0, we have a vector that's pointing negative 2 in the x direction. At 1, 1, that's this point here, we have a vector that is pointing negative 2 in the x and 3 in the y. So we're going to be doing one of these. At negative 1, we're going positive 2 on the x and still 3 up on the y. So we're doing one of those. At 2, comma 2, we're going negative 4 and 12. So we're doing one of these. This, I don't think, gives us a very good idea of what this graph looks like. So let's do some more points. Let's take this one right here. At positive 1, comma negative 1, we're still going to be going 2 units backwards. And we'll still be doing 3 units up. So this is another one of these. At this point right here, this is negative 1 on the x, so we're going 2 forward. Positive 1 on the y, so we're still going 3 up. We're doing one of these. Let's go out to some 2's on the x-axis here. At 2, 0, we have this vector for negative 4. I bet at negative 2, 0, we have a vector for that way. So we have this sort of symmetry across the x-axis where things are going like crisscross. If we go positive 2, negative 1, we should have a vector that's pointing 4 backwards and 3 up. If we go out to here, we should have a vector that's pointing 4 to the right and still 3 up. I feel like at some point I'm just making a mess of this. Things crisscross. This 3y squared piece means that these vectors are always going to be pointing up-ish. This j component can never be negative. So on the x-axis, the j component is 0. All those vectors are horizontal. They all point inwards. As you increase your y values, you're going to get things that are increasingly pointing up. As you decrease your y values, you're still going to get things that are pointing up, because y is getting squared here. Negative x here means that everything is going to be pointing sort of vaguely backwards. So if you move to the right on the x-axis, your vectors will point back to the left. If you move to the left on the x-axis, your vectors are going to point back to the right. And you get this crisscross pattern, that everything is pointing towards the y-axis and moving upwards. So that's the vector field. That's this particular vector field. This one came out a little messy. Hopefully you still kind of have this general sense of this. And I'm making this gesture with my hands because the thing that we're going to use vector fields for are force fields and flow. So you can imagine you want to be able to imagine some sort of particle or some sort of marble or some sort of like, if you want to imagine this as like the flow of water. Maybe you have a lot of water pouring in from the sides and it's vaguely downhill in this direction, so things accelerate that way and things are coming in from the sides. You want to imagine like maybe a little paper boat. If you put a paper boat somewhere on here, it's going to get pushed in this direction. If this is a magnetic field, I don't know if it's possible for this weird crisscross thing to be a magnetic field, but if this were a magnetic field and you dropped an iron marble in there, it would move in this direction. Or if you dropped it over here, it would move in this direction. If this is airflow, if you have a bunch of fans that are all sort of pointing this way, and you released a feather somewhere, it would move in this direction. It would follow a path that looks like this. And that's what we're going to use these things for. We're not going to talk about paths quite yet. We'll start doing paths in the next section when we talk about line integrals. But I do want you to be sort of thinking about paths as you're doing this. So we kind of want to be thinking about, if you take an object that has no inherent mobility, like a steel marble in a magnetic field or a little paper boat on some water, what will happen to it? We also eventually want to be thinking about, if you take an object that does have some mobility power of its own, like if this is a really big water flow and you put like a toy boat with a motor on it, and you want the toy boat to go from here to here, like against the flow or like across the flow, we want to be able to figure out how much power is necessary, how much force this little toy boat needs to exert to move itself across a path that isn't just the path this thing is pushing it on. So those are the kinds of things we're going to be doing with vector fields. For the rest of this section, I just want to give you more examples of vector fields. We can figure out what they look like, how they behave, what kind of paths they create. There's some that appear pretty frequently, so we'll give those names. And then we'll figure out how to determine whether vector fields are sort of perpendicular or parallel to certain curves or certain paths. But for now, I just want to do some more examples of vector fields. I think we're at 13 minutes. I think we have time for one more example, and then I'll cut this video, and then we can do some more examples. Okay. So that last one was, I think, probably a decent introduction because it came from a gradient. We know about gradients. We've worked with gradients before. I want to do an example that comes from just a regular vector field. And I want to show you my favorite vector field. My favorite vector field is negative y comma x. And to explain why this is my favorite vector field, we're going to have to draw it. So I'm going to make a big table here, x, y. I can play with both of these, and then I need f is going to be my vector. So I like to start with like the basic 9, I guess. Yeah, basic 9 is 0, 0, 1, 0, 1, 1, 0, 1, negative 1, 1, negative 1, 0, negative 1, negative 1, and 0, negative 1. Is that the 9 I want? 1, 2, 3, 4, 5, 6, 7. There's one more I'm missing. 0, negative 1. So, 1, negative 1. Okay. These are the 9 points, the 9 grid points that are all like one unit to the left or right, up or down of the origin. So let's figure out what this function looks like at each of these points. At 0, 0, my vector is going to be 0, 0. At 1, 0, my vector is going to be 1 on the x, which should give me 0, comma 1. At 1, 1, I will have negative 1, 1. At 0, 1, I should have negative 1, comma 0. Negative 1, 1 should give me, negative 1 is the x value here, so that would give me a negative 1. Wait, what? Negative 1 is my x value, so that puts a negative 1 here. 1 is my y value, so that will put a negative 1 there. Okay. Negative 1 comma 0. 0 is my y value. Negative 1 is my x value. Negative 1 should put a positive 1 here and a negative 1 there. 0 comma negative 1 should put a positive 1 and then a 0. And 1 comma negative 1, this is the other tricky one I have to think about. Negative 1 for an x value means that this is going to be positive 1. Sorry, positive 1 x value means I get a positive 1 for my j component. Negative 1 for y value means that I get a positive 1 for my y component. So let's see what this looks like so far. 0, 0, let me... At 0, 0, I have no vector. At 1, 0, that's this point, my vector is pointing straight up 1 unit. At 1, 1, this vector is pointing left and up. At 0, 1, this point right here, my vector is pointing straight left. At negative 1, yeah, here we go. At negative 1, 1, that's this point here, my vector is pointing left and down. At negative 1, 0, my vector is pointing straight down. At negative 1, 1, my vector is pointing left and down, right and down. At 0, negative 1, my vector is pointing straight right. And at 1, negative 1, my vector is pointing this way. This is the general shape of the thing. And the size of these vectors depends on how far away from the origin you get. So if you wanted to do more vectors really close to the origin, you'd get these same shapes. They would just be smaller. If you want to do vectors really far away from the origin, like I can probably fit this vector on here. This is the point 2, comma 1, and that would give me hold on, negative. Oh, yeah, negative 1 on the x. Yeah, this point 2, comma 1 is giving me a vector that goes negative 1, comma 2. So it's going to go left 1, up 2. This whole vector field makes a big spiral. I don't know if this vector field has an official name. My personal name for this vector field is the toilet flush. Because it looks like a toilet flush. Things just go around in circles. And I think that's very cool. This vector field doesn't make a vortex. So like, toilet flush isn't the perfect name for this, because you can see that it's kind of pushing things outwards. Like if you dropped, if this was a water flow and you put a boat here, it wouldn't get sucked into the middle. It would kind of get pushed towards the outside edge. But it does get pushed outwards in a spiral. So I think that's pretty neat. I'm not sure how you'd actually make something that like pushes things inwards. This just kind of pushes things around. So